Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to write molecular, complete ionic, and net ionic equations for different reactions. In this video I'm going to go over how to do them for iron 2 carbonate reacting with hydrochloric acid. So let's get into this. So iron 2 carbonate and hydrochloric acid, those are the two reactants that we're looking at. We have them here in their names. We're given the names, we need the formulas. So you need to know how to go from the name to the formula. If you are struggling with that or need help with that, please see my videos on naming ionic compounds. I'll link them in the description. So let's go over how to do that here. So for ionic substances, so this is an ionic compound. We could tell by the way it's named, iron 2 and carbonate. So the way that names work for ionic compounds is that if the name of the compound comes from the name of the ion. So if you know the two names of the ions, you just put that together and you get the name of the compound. So in this way, we're working backwards. So we take the name of the compound and we break it apart into its two parts. So the two parts of the name of the ionic compound are the names of the ions themselves. So here we have the iron 2 part, that's the iron 2 ion, and then we have the carbonate ion. So this ion here, iron 2, obviously it's iron. So the symbol for iron is Fe. And the 2 here, the Roman numeral 2 always tells us the charge on the metal ion itself. So this is not telling us the number of ions we have or the number of atoms of iron we have in our compound. It's only giving us the charge. So this is going to be a 2 plus charge on our iron. Carbonate is a polyatomic ion. So you need to know the polyatomic ion formulas and their charges. I'm sure your teacher is giving you some sort of polyatomic ions sheet or common polyatomic ions that you're going to need to know. If you're struggling with that, I have a couple of videos on how to memorize them, and I show you patterns. So that'll be linked in the description as well. So carbonate ion, you have to know, is CO3 with a 2 minus charge. So now that we have our two ions here, now we just need to put them together into a formula, and that's where we're going to need to balance the charge. So you'll notice here I have a 2 plus charge here, and I have a -1 charge there. So all I need is one of each to balance the charge since they have equal charge. Another way you could do it is you could do the crisscross method. So here you could take the 2, and then you could put that as a subscript there. You take this 2, put it as a subscript there, and then you'll end up with Fe2CO3 in parentheses 2, and that would be a balanced formula. However, there's a problem here. So you have to be careful when you're doing the crisscross method, and you need to double check that the subscripts here, the 2 and the 2, are in their smallest whole number ratio. So 2 to 2 is not the whole smallest whole number ratio. It can be simplified. So you could simplify this to 1 to 1. That would be the actual proper formula. So it would be FeCO3. So you want to simplify this to FeCO3. So you'll notice that when I had more than one carbonate ion, I use parentheses. So whenever you have more than one polyatomic ion, then you're going to need to use parentheses around the polyatomic ion, and you're going to put the number, the subscript on the outside to indicate how many you have. When you only have one, there's no parentheses. So here I only have one carbonate ion, so there's no parentheses used. So here's my formula for iron carbonate, or iron 2 carbonate. What about hydrochloric acid? So obviously this is an acid, so you're going to need to know how to name the acids. I also have that linked down into the description if you need help with that or need a refresher. There's two kinds of acids. The main kinds of acids are binary acids and oxyacids. The oxyacids are basically come from the polyatomic ions that have oxygen in them, like sulfate, sulfite, nitrate, nitrite, those type of polyatomic ions that have oxygen. The other type is the binary, and you can always tell the binary acid from the beginning. So if it begins with hydro, that's a definite giveaway that it's a binary acid. So here we have hydro, so that's a binary acid. And the binary acid, it means that it has two atoms or two ions that make up the acid. And one of those has to be hydrogen because it's an acid. So hydro stands for the hydrogen, and then the other part tells you the other element involved. And here it's chloric, so that means it's chlorine. So we have hydrogen and chlorine. So that's going to be HCl. So we have HCl for the formula for hydrochloric acid. So now that we have the formulas for our reactants, we can now go ahead and predict the products. So here, the way we're going to predict the products is we can see here we have a ionic substance here, and we have an acid. Now the acid here this is a strong acid, and acids in general, they'll break apart into ions. They'll ionize in water. So they're kind of behaving like ionic substances, even though acids are not ionic substances. They're molecular substances that will ionize. So here, I'm going to put this down here. So we have HCl. So this would be the proper formula. So we're going to get rid of that. All right, so here, if we treat this as an ionic substance and this is an ionic substance, then this is a dead giveaway for a double displacement reaction. So what's going to happen in a double displacement reaction is the inner ions will go together and the outer ions will go together. So that's the way we're going to write our products. So our possible products are going to be where the iron 2 ion comes together with the chloride to form a product, and the hydrogen and the CO2 or CO3, the carbonate, is going to come together to form a product. So iron, we need to balance the charge. Iron has a +2 charge, and the chloride ion has a -1 charge. So we're going to need 2 chlorides to balance the charge on your iron. So that's going to be FeCl2. And then we have hydrogen, that's going to be H+. And then we have our carbonate ion that is a 2- charge. So we're going to need 2 positive H's to balance the charge for our carbonate. So that's going to be HCO3 or H2CO3. And so now we have the formulas for our products. So the next thing we need to do is balance the equation and then determine what the states of matter for each of these are. So let's go ahead and balance first. So I have 1 iron here, I have 1 iron here, so that's balanced. I have 1 carbonate here, I have 1 carbonate there, so that's balanced. I have 1 hydrogen here, but I have 2 there. So I'm going to need to put a 2 coefficient here. So now that's balanced. And now I have 2 chloride ions, and here I have 2 chloride ions. So that's balanced there. So now we have a balanced equation. So the next thing here is to determine the states of matter. So here, carbonates, we got it when you do your when you want to figure out what state your ionic substance is in. This is where the rules come in, the solubility rules. So according to solubility rules, if we look at carbonates, it says salts that contain carbonate are insoluble unless it has a group 1 element or ammonium. So group 1 element or ammonium. Are there any other rules we need to worry about here? No, so that's the only one. So here, iron, we have iron that is not a group 1 element, so iron carbonate. So carbonates generally are insoluble unless you have a group 1 metal. And so here, this is going to be a solid. And then here we have hydrochloric acid. Hydrochloric acid is going to be aqueous. So that's going to be AQ. And then what about chlorides? Chlorides here, it says are chlorides, bromides, iodides are soluble unless they are with silver or a lead 2 ion or mercury 1 ion. And we don't have that here. So that's going to be soluble. So that's going to be aqueous. So we have aqueous here. And here, you have to recognize this as an acid, right? It begins with H plus, it begins with hydrogen. We have H2. This is an acid. This is carbonic acid. This is actually a weak acid. It's going to stay together. That'll be aqueous. So we could write aqueous, right? But notice that these are both aqueous, and so we might be fooled in saying that, oh, these are aqueous, they're gonna fall apart. This is actually probably gonna stay together since it's a weak acid. Weak acids stay together; they don't really break apart all that much. But also, there's something special about carbonate. So anytime you have a carbonate reacting with an acid, you're gonna get some sort of you're gonna get carbonic acid. But whenever you have a carbonate as a product, you have to watch out for the decomposition of that into carbon dioxide. So in here, this is actually going to break up into carbon dioxide and water. So the products here are actually going to be CO2 gas and then H2O. So this is a gas evolution reaction. So this is definitely something to watch out for. So pay attention to carbonates. They can break apart into carbon dioxide and water. So this would be the actual products of this reaction. So if we were to put this together, you should see bubbling occurring in your reaction vessel, and that bubbling would be because you're forming carbon dioxide gas. Okay, so this would be our balanced equation. And so here, this is our balanced molecular equation. Now for the net ion, for the complete ionic equation, let me fix that. So for the complete ionic equation, now what we're going to do is we're going to break apart the ions into their separated ions. If it's an aqueous ionic substance, we're going to break those apart. If it's a gas, a liquid, a solid, those are going to stay together. Only the aqueous ionic substances will come apart. Anything that's a weak acids stay together. Anything like a weak base. Bases and acids that are aqueous usually will stay together if they're weak, right? Strong acids and bases, if they're aqueous, you can break those apart as well. So what do we have here? We have a solid here, so that's going to stay together. So the FeCO3 solid, that's going to stay together. This is a strong acid, so that's going to stay together. So that's that's going to fall apart. So that's going to be completely separated. So we're going to separate this into H plus and chloride ions. So that's going to be 2H plus aqueous. And notice that I'm writing the charges of the ion. So when you separate the charges into a complete ionic equation, you write the charges when you're separating the ions. Here, when the ions are together or when they're together in a molecule like this, there's no charges here, so you don't write the charges. Here, this is ionic substance. There are charges, but we don't write the charges when we're doing the formula. So here, this is going to be plus 2 Cl minus aqueous. So here we've got our reactants separated except for the solid. Now we're going to do our products. This is an aqueous ionic substance, so those ions are going to come apart. So we have 1 iron 2 plus aqueous. And here, the product is water. So water is a liquid and carbon dioxide is a gas. So those are going to stay together. Those will not come apart. So we'll write H2O liquid plus CO2 gas. Okay, So that, ladies and gentlemen, is our complete ionic reaction. We've separated all of the ions that can be separated. We separated all the atoms, or the atoms that can be separated from your hydrochloric acid. And so here is our complete ionic equation. So the next thing you want to do is your net ionic equation. And so for your net ionic equation, you're always going to separate out the what are called the spectator ions. And the spectator ions are the ions that are not doing anything. They're not involved in any reaction. So there's a couple ways you can identify these spectator ions. The first way might be that you would go to the product and see, okay, what over here participated in forming the product over here. So if you find something over here that is participating in the making of the product over here, then that is not going to be a spectator ion. You want to keep that. If anything over here is not involved in any product making, then that's going to be a spectator ion. The other way is you can look at both sides of your arrow. You can look at the reactant side and the product side and see what stays the same, what doesn't change on both sides. And if it doesn't change and it stays the same, then that is a spectator ion, and you can eliminate that from your complete ionic equation. So here we have a solid iron carbonate, but here we don't have solid iron carbonate. So iron and carbonate are no longer in a solid. So both of these are involved in the reaction. So these are not spectator ions. Here we have 2H plus aqueous. Over here, we do not have H plus aqueous. So this is involved in the reaction as well. Here we have 2 chloride ions aqueous. And here we don't have our chloride ions. Oh, I forgot to put the chloride ion. So let's put that in. So here we go. I forgot. Skipped over that. So that's going to be plus 2Cl minus aqueous. There we go. I was jumping the gun. So here we have our 2 chloride ion aqueous, and we have our 2 chloride ion aqueous. So that stays the same. So there's no change from here to here. So that is a spectator ion. So we can get rid of that. And that's it. So all of this here is involved in the reactions here. So the only spectator ion is our chloride ions. So we get rid of those. And so when we write our net ionic equation, we write everything except for the spectator ions. So here we have FeCO3 solid plus 2H plus aqueous. And that's going to go to Fe2 plus aqueous, and then no spectator ion, so plus H2O liquid plus CO2 gas. And so that would be our net ionic equation. So I hope that was helpful. Sorry about the confusion here. If you learned from this, if you enjoyed the video, please like the video, subscribe to my channel, hit that notification bell, and put a comment in the comment section so you can tell me what you think, and if you have any questions that I can answer. Thanks for joining me, and have a great day.